Okay, pre-cal 12, here we go. Let's get after it. We are diving into trig basics. Now, bear in mind, this is trig basics for grade 12. We've already covered trig in both pre-cal 10 and pre-cal 11. So we're going to be tying in some of our vocabulary and concepts from those courses. But here I'm going to introduce a little bit more. So the first bit's here, a bit of a refresher. If you look, we have our Cartesian plane, which is this baby here, right? It's made up of 4 quadrants. The quadrants are going to become very important as we work through this in the next few videos. So let's identify the fact that they are indeed quadrant 1 here, and then we go counterclockwise. 2, 3, 4. Those are our 4 quadrants. All right. Now, oftentimes people go, well, why do they go that way? Well, it comes down to the next thing we're talking about, which is the terminal arm. So the terminal arm is our arm that demonstrates our rotation, and it originates from the origin, and it looks like that, right? And it could sort of be anywhere as it rotates. The thing is that terminal arm rotates in a counterclockwise direction because the angle here and then here and then here and then here increases. We are opening up the terminal arm. So the terminal arm sweeps around and it rotates through all 4 quadrants as it goes around and around and around, right? So you can see that the terminal arm rotates almost into a full arc, and then eventually, yes, it will do a full 360-degree arc. So that is why we count counterclockwise, because we start here and we rotate our way through to the second quadrant, then the third quadrant, then the fourth quadrant. Now, standard position just means we have a terminal arm originating from the origin, rotating from the x-axis. So that would be in standard position. As it rotates, so if our arm ended up here in quadrant 2, that's standard position. And it just means we have a big angle here, an angle greater than 90 degrees. And then if it were to rotate into the third quadrant, well, again, that's still standard position. We just have a large angle here, which is greater than 180 degrees. So the angle in standard position is always measured from the original positive side of the x-axis. So those are your first warm-up ones. Now, when you are rotating in a counterclockwise direction, you have a positive degree. So let me just draw a couple examples on here. If we have rotated to here, this is 45 degrees, positive. If we have rotated to here, and obviously I just made up the 45 degrees, but let's get the gist. Here, this is anywhere between 90 and 180, so let's just say this is about 150 degrees, positive. If your line were to rotate in the negative direction, so this way, we're rotating clockwise, so not standard position if you're counting it as a negative rotation. So this would be negative 45 degrees. Now, obviously, this still has a positive counterpart, and we'll talk about that in a minute. But if you rotate your line in a clockwise direction, you get a negative angle of rotation, which we don't really use. We then use what's called coterminal angles to get its positive value, but we'll get to that in just a minute. But do know that you can rotate a negative rotation. It just takes you the other direction. So it puts you in different quadrants depending on the negative degree. So next, coterminal. So this is what I was just talking about. So if you think about where our angles exist, so for instance, this one right here, 45 degrees, right? Boom. Well, if that arm were to sweep all the way around another 360 degrees, it would finish there. Well, that green angle, including the original 45, would be 45 plus 360. So we would get 45 plus 360, and the green angle represents 405 degrees. Now, if you were to take your calculator and pick sine, cos, or tangent, and key in 45 degrees or 405 degrees, you would get the same result because the terminal arm is in the same position. You've just done multiple rotations. So a coterminal angle is an angle that has the same ratio value when used in trig functions. It just has 360 degrees added or subtracted to it. So let's look at another one. Imagine you have the angle negative 320 degrees. Okay, so negative 320. So that means we've rotated a negative direction. We've rotated 90 degrees. We've rotated 180 degrees. We've rotated 270 degrees. So we're in here somewhere, right, at about negative, because we rotated the other direction, 320 degrees. Well, what is that as my positive value? Well, why don't I just take this arm, swing it around this way, 360 degrees. So I'll add 360 degrees to that negative 320. What do you get? You get 40. So 40 degrees is a coterminal angle to negative 320 degrees. They will both produce the same value because the arm is in the same position. You just have 1, 2, 3, 4, 7, it doesn't matter, more full rotations. So let's do one more here so you can really get that idea of coterminal. And just say, okay, where would I draw my line if I had degree of rotation of 3,000 degrees? So if I have rotated 3,000 degrees, well, if we take 3,000 and we divide it by 360, we get 8 and a decimal value. So let's take 8 and multiply it by 360 degrees. So what that tells us is how many full rotations is 360 degrees. It's 2,880. So that means of that full 3,000, 2,880 were just excess rotations. And if we do that subtraction, we're left with 120 degrees. So it means that our line located at 120 degrees, so 30 degrees past 90, so that angle there at 120 degrees is the same as the angle with 8 more rotations. So I'm not going to draw it on there, it'll get pretty messy, but if you took that line and you rotated it 8 times all the way around, you'll get 3,000 degrees. And that's why coterminal angles are helpful, because this is a much easier angle to deal with and it makes more sense visually as well. So to get coterminal and angles, both negative or positive, you just kind of wind up what you're given. You unwind it by 360 degrees or you wind it up by 360 degrees. And what I mean by that is if you have a negative angle, you're going to wind that terminal arm 360 degrees until you end up in a positive angle. So there's lots of examples of that in your notes. Have a look through coterminal. It's helpful to get to angles between 0 and 360. So next up on the docket, reference angles. Probably the most important thing we can look at here. Reference angles are angles when the terminal arm is in standard position. Okay, so standard position. But reference angles are acute angles with the x-axis. Positive acute angles with the x-axis. So you get terminal angles in each quadrant, reference angles with the terminal arm. So here's terminal arm in quadrant 1. Here is the angle that is created by the rotation. That is our reference angle. And I'll just say theta with a little r, because that is my positive acute angle with my x-axis. Now, as that terminal arm continues and swoops through into quadrant 2, this is my theta, right? That full rotation. And now I'll just erase quadrant 1 so we're not getting all confused. That is my full rotation. That's my theta. But my reference angle, that's not an acute angle, right? That's not less than 90. That's greater than 90 degrees. So my acute angle is the angle that is created here. So my reference angle is that. And how do we calculate that? Well, we calculate that because we take 180 degrees, which would be a full rotation right to here, and we subtract our standard position theta. And we get our reference angle in quadrant 2. So let's put some actual numbers into play there so you can make sense of it. Let's say we have theta that is equal to 150 degrees. Well, that means I have an angle of rotation all the way to about here. That's 150. Well, what's left? Well, 30 degrees. So the reference angle there is 30 degrees. Now, we looked at in grade 11, the relationship between reference angles and angles in standard position. And a lot of it is now going to come down to what quadrant we're in due to which trigonometric function we're using, but we will see more of that as we go. And if you want to see a little refresher, you can always go back to the pre-cal 11 video for that. So for Q2, It's 180 degrees minus theta. Now, when we get into Q3, well, we're here. So again, here's theta comes all the way to here this time. Well, what's my acute angle with the x-axis? It's just this chunk right here. So this chunk is my reference angle. And how do I get that in this example? Well, it's 180 degrees plus, or sorry, not plus. We have 180 degrees, and that's what gives us theta. It's going to be theta minus 180 degrees, right? It's this entire rotation, and then minus this chunk only of the rotation. Take the 180 away, and we're left with our reference angle. And then lastly, we end up in quadrant 4. And when we're in quadrant 4, well, this time our standard arm goes all the way to here, and our acute angle is made right here. There's my reference angle. So how do I get that? Well, that is 360 degrees minus theta. So you will have reference angles in every single quadrant, right? So, and you will have the same reference angle in every single quadrant. So in the notes, I've done examples of varying degrees, but I'm going to do a little different ones here. I'm just going to show you that you can have the same reference angle in each quadrant, and that actually changes the standard position angle. So let's make reference angles here of 45 degrees, reference angle of 45 degrees, reference angle of 45 degrees, and a reference angle of 45 degrees. Right, so all of these have lines, and obviously they'd be given either independently, have a reference angle of 45 degrees. Now for quadrant 2, we go 180 minus 45, and we get the standard position angle of 135 degrees. For quadrant 3, we're going to take 180 degrees and we're going to add 45, and we get 225 degrees. And then we're going to take 360 and subtract 45, and we get 315 degrees. So what you would notice is if you took 45, 135, 225, and 315, you get the same ratio of your trig function. Now bear in mind, the same ratio, because the sign will change. The positive negative sign will change. So just as an example, if you wanted to plug these into your calculator, you would get the same ratio for 45, but you would get a positive value here, a positive value here, a negative value here, and a negative value here. And we're going to talk about that more in the next video. And it was looked at in 11, but we're going to talk about that more in the next video as well. But be comfortable and confident with your reference angles. They're going to come back again and again and again and again and again. Okay. So let's do those 3 examples that I promised from the book. So find the reference angle for 200 degrees. Well, where's 200 degrees? It's slightly past 180. So if that's 200 degrees, well, what's my reference angle? What's this angle in here? Well, remember, it's theta minus 180. So 200 minus 180, I get a reference angle of 20 degrees. So what about 300 degrees? Well, where's 300? Well, 300 degrees is in quadrant 4, because that's 270, and then boom, 300. So that's 300 degrees. Well, how do I get that one? Well, it's going to be 360 minus 300. I get a reference angle of 60 degrees. And then negative works just the same. If we rotate negative 200, well, that's negative 90, that's negative 180, that's negative 200. So negative 200 is there, but my reference angle is right here. So what's my reference angle? Well, first off, that negative rotation doesn't really help me out. So let's use a coterminal angle to go 360 plus negative 200. So we're taking that negative 200 and we're rotating it back around so that our angle of rotation actually looks like that. And we get 160 degrees. So what we've done is we've changed that sort of path of rotation from a negative direction to a positive direction. So we're looking at that. And that's why coterminal angles are super helpful, because it's easier to grasp it with respect to negatives. Because now what's a reference angle? Well, easy to see in here, 20 degrees. So those are reference angles. Now let's jump into the new thing for this section, radians. Radians and the unit circle. So as we move into our trig here, we're kind of going to stop talking about degrees, and we're going to talk a lot more about what are called radians. So what are radians? Well, radians measure the distance that your terminal arm has covered. So this portion is going to give you what's called an arc length. Okay, I have it here. Now on the unit circle, you get an arc length of 1 when you've rotated 1 radian. But that's what's going to change. The radian is the rotation measure here instead of a degree. So what you get is as your radian increases, your arc length increases. So by using radians, it allows us to calculate the distance traveled of an arc. So it's going to come in super handy. And its radians have a direct correlation to degrees. So we're going to look at how they're related, but you're going to want to get really comfortable with radians. We're going to start talking almost solely about radians because it gives us a numerical value to calculate with. It's kind of like how we convert percentages into decimals. Well, converting degrees into radians allows us to calculate with them a little bit more efficiently. So how do we come up with radians? Well, if you look at the circle there, the big thick circle, it has a radius of 1, right? And if you take a full rotation of a circle, you have 2 pi, right? Full circumference, full rotation is an arc length of 2 pi because the unit circle has a circumference of 2 pi. Because in the unit circle, our radian is 1, right? Our radius is 1. And if you remember, the circumference of a circle given right here is 2 pi r. So what's the measurement of the circumference of a circle when you have a radius of 1? Well, it's 2 pi times 1. So that means radians is 2 pi to 360 degrees. So that's our ratio, but we can simplify that to pi to 180. So that's the relationship to radians to degrees. It's either pi over 180, depending on what you want to convert, or 180 over pi. All that means is that is the ratio of radians to degrees. And we will use them depending on what units we're trying to get to. Unit cancellation with radians and degrees works the same as it did with centimeters and meters, for instance. So there's our ratio, pi to 180. Let's actually use it. So if you have 315 degrees, you want radians. So you're going to go, okay, my degrees are on top, which means my ratio is going to have degrees on the bottom because I want to be left with radians. So we have pi over 180. Now, you could multiply and divide, get a decimal, but it's also nice to leave your answers in pi form if you can. So you'll notice that simplifying 315 over 180 as a fraction leaves you with 7 over 4. And then don't forget your pi. So 7 pi over 4. If you have 35 degrees, well, again, it's 35 degrees times pi over 180. Well, in this case, 35 and 80 cancel out. We're left with pi over 4. You could crunch that number and you'd get an approximation, 0.79. But you're going to see that we're going to use these more often than not. So it's better to be able to simplify the degree portion of your fraction. And if you get a fraction result, then you have a radian that can be written with pi included. Otherwise, you're going to have a big decimal. Now, when I say simplify, almost always you can simplify your fractions, but if you didn't, you could have something like 315 pi over 314. Well, yeah, that's weird. You would do that calculation, over 315 over 180 simplified out, right? But what if you had something like 23 over 180 pi, right? That's not going to simplify as a fraction. It's just 23 over 180. Well, then you could, sure, calculate that into a decimal. But you're going to notice that most of what we end up dealing with are going to be some simplifiable, that's a new word I just made up, radian numbers. Because we're going to see some pretty good patterns with degrees that we're going to use, particularly when we get into special angles. But you can see for the radian examples, we have both. For the first one, we have 5 pi over 6, and we want that as degrees. So now this time we have the degrees on top, and we have the radians on the bottom. So you'll notice the pi's cancel out. So in this case, we end up with 900 over 6, which simplifies to 150 degrees. Now in this case, right? There's no pi here because this is a radian measure, but we've done the calculation. So you still have 2.5 radians, so it's the same equation. 2.5 times 180 over pi. And then we have 2 times 180, and we divide by pi. And in this case, we get a decimal, which is going to be 143.2 degrees. So you can't always just cancel out the pi's if there's no pi given. You can have radian measures like 2.5, like 0.3. You can have radian measures that do not have the pi symbol included in them. They are just calculated out because radians are numerical values in between 0 and 2 pi of one rotation. So you can have kind of anything in between there. If you think, remember, pi is 3.14 and a whole bunch. 2 pi is going to be 6.28 and a whole bunch. So you can have radian values representing any numerical value because you can rotate in a negative direction as well. So be aware of that. Radians don't always look like that. Sometimes they look like that. Now, the last piece is arc length. So why we care about radians is because they help us calculate the arc length, the length traveled by the end of the terminal arm. So here to here, that is my arc length. What distance have we traveled in that rotation? So it's a pretty simple equation. Don't ask me why they use the letter S for arc length. It's kind of confusing, but we're going to go with it. So S is the arc length, R is the radius, but then theta is your central angle. So geometry term, central angle is in here. It's the angle made at the center of your circle. And theta is given in radians. So if you don't have theta in radians, you have to calculate to radians first. So here is an example of how this works. Determine the arc length of a circle with a radius 6 and a central angle of 45 degrees. So that means we have a circle and we've traveled 45 degrees from here to here. Right? Here's the distance traveled. And we want to know, what is that distance? Well, 45 degrees isn't going to work. We're going to need radians. So we take our 45 degrees, we multiply it by pi over 180, and we're left with pi over 4. So now we have a radian measure for our angle of rotation. And now we can use our equation. We have a radius of 6, so arc length is equal to radius times theta, and we get 6 times pi over 4, which gives us 6 pi over 4, which is 3 pi over 2, which is 4.71 centimeters. So we have rotated 4.71 centimeters. So that is when we use arc length. So 2 more. Find the distance traveled by the tip of the second hand of the clock with a radius of 13 centimeters. So this might help visually if you don't look at analog clocks anymore. The second hand is going to travel from there to there. Okay, and how far has it traveled? Well, that's 30 seconds of a possible 60 seconds, which is half of a revolution. And if a full revolution is 2 pi, that means it's traveled pi radians. And the radius of the second hand is 13 centimeters. It's a pretty big clock. So we have everything we need. So our arc length is going to be 13 times pi, which we calculate out at 40.8 centimeters. Done. So just be aware of rotation around a clock. Remember, a full rotation is 60 seconds. So if you're dealing with seconds and you're following the second hand, then you're using a fraction out of 60 to determine the distance of revolution. It's possible you have, say you only wanted 20 seconds. Well, that would be 1/3 of a revolution. So that would be 2 pi times 1/3. So that would be 2 pi over 3. So you can see that the distance of your revolution changes. So just be aware of that with clocks, because you'll see questions with clocks often. So then the last one, what degree, so this time we're going to work backwards, is the central angle if the arc is 24 centimeters. Okay, so now we have an arc of here, 24 centimeters. And we have a radius of 5 centimeters. Well, this is just algebra working backwards, right? But be careful because this says what degree measure. So we have arc length is equal to radius times theta. So in this case, we have 24 is equal to 5 times theta. So 24 over 5. And remember that that's going to give us data in radians. So that gives us 4.8 radians. And then since we want degree, well, we take our 4.8 and we multiply it by 180 over pi. 180 over pi. And calculate that through, and you get 275 degrees. So play around with this section. This section is all about understanding those circles of rotation. So standard position, terminal arm, reference angles, and then it dives into radians, degrees, their relationship together, and then arc length. Get as comfortable as you can with this because our next video, we're going to start taking all of this stuff for granted and we're going to start using it in all of our scenarios that we work through. Okay, thanks so much. I'll see you next time.